Hello. In this video, I'm going to work through an example on the calculation of uncertainty. This is a very typical problem. The oscillation of a pendulum is used to calculate the value of g, the acceleration of free fall. The time for 20 oscillations is measured with an uncertainty of 0.1 second, and the length of pendulum is measured with an uncertainty of 0.1 cm. So the uncertainties in T and L is going to fit into the uncertainties of the calculated value of g. That's why this question asks us not just for the calculated value of g, but also its associated uncertainty. The first thing we do is, of course, to make g the subject. Basically, we square both sides of the equation, throw g to the left side, and throw t to the right hand side, and we arrive at this equation here. We can plug in the numbers. Notice that I've divided the time for 20 oscillations by 20 in order to obtain the value for the time for one period, which is the time for one oscillation. And so I arrive at their number here, 9.8207. At this stage, I do not know how many digits I'll need, so I'll just keep more. The next thing we do is try to obtain the value of the uncertainty in g. But when we look at this equation, we see that g is calculated by multiplying up terms, not by adding up terms. So we will not be adding up the absolute errors, but instead we'll be adding up the fractional errors. So the fractional error in g is the sum of the fractional errors in L and T. Of course, because of the power of 2 here, the fractional uncertainty in T has to be multiplied by 2 because of the power of 2 here. 4 pi squared is just a constant, and it does not affect the fractional uncertainty in g in any way. We next plug in the numbers. Now you will notice that for delta big T over big T, the numbers I put in is actually the numbers for delta small t over small t. I do that because I know these two are really the same numbers. Let me explain quickly. Now the time for one oscillation is calculated by taking the time for 20 oscillations divided by 20. When we do that, the absolute uncertainty in T is also divided down by 20 times. When you see that, it should be clear to you that the fractional uncertainty for one oscillation is the same as the fractional uncertainties for 20 oscillations. Having obtained the fractional uncertainty in g, I just need to multiply it with the value of g to obtain the absolute uncertainty in g. We now put the two numbers together, but this is not the end. Remember, by convention, we always write the absolute uncertainty to just one significant figure. So instead of 0.15556, we just have to write 0.2. And one last thing, by convention, we'll write the value of g to the same precision as its uncertainty. Since our uncertainty is written to one decimal place, we will also round off this number to just one decimal place. So that's it. Ta-ta!